Hello. So today let us discuss a few questions based on optical isomerism and geometrical isomerism. So we have 17 questions today and most of them are basic level. And in the next part 2 video, let's see some advanced level questions. So let's see the basic level questions. We have 17 questions. Let's start. The first question, which of the following is optically active? Right? So let's draw the structures. So you have one bromobutane. So this is butane, one bromobutane. So one bromobutane, you have hydrogens everywhere. So when you have the same atom on the carbon, it won't be chiral, right? On a chiral carbon, all groups should be different. So one bromobutane is not optically active because it does not have a chiral carbon. Now, two bromobutane. So you have like butane here, two bromobutane. Now, here we have a chiral carbon because we have a CH3 group, one ethyl group, one bromine group, one hydrogen. So all three groups are different. It's sp3 hybridized. So it is optically active. You can check the other options also. No. Which of the following operations on Fisher formula? We have given this Fisher formula here does not change its absolute configuration. So when it comes to absolute configuration, when you do, so the key point here is when you do two group exchange, even number of times, the configuration will not change because internal compensation takes place. So when you do odd number of times, like you shift it one time, so you do one time two group exchange. Like these two groups I am exchanging. One time I am doing two group exchange. So you have to write the reverse configuration for the correct answer, right? So now for absolute configuration, two group exchange even number of times will not change the configuration. So exchanging groups across horizontal bond. What does it mean? You are doing two group exchange one time. So it would change the configuration. Okay. They are asking does not change the configuration. Changing groups across vertical bond. Yes, here also you are doing a two group exchange one time or odd number of times. So it would change the configuration. Exchanging groups across the horizontal bond and also the vertical bond means you are changing these two, one exchange and these two, another exchange. So when you are doing two group exchange two times, because of internal compensation, the absolute configuration remains the same. So C will be your correct answer. And exchanging a vertical group and a horizontal group, that is also a two group exchange one time. It would change the configuration. So the correct answer will be C. Let's look at the third question. Which of the following shows optical isomerism? Draw the structures. Now you can clearly see, check for the chiral carbons. In the option A, you don't have chiral carbons because each carbon has minimum two hydrogens. So when you have same number of groups, more than one on the same carbon, same group, like you have same group A and A on the same carbon, so it will not be a chiral. So the condition for chirality is all groups should be different, sp3 hybridized. So this does not show optical isomerism. So let's look here. So you have CH2, you have a OH attached here, and you have CHO. CH. Okay. Oh, no, no, no. It's something like, right. CH2, OH, and then CH, and then OH, EHOH, and then you have CH2 and OH. See, you have two hydrogens here. This is not a chiral. You have two hydrogens here. This is not a chiral. And when with respect to this carbon, you have an OH, you have an H. But these two, this alkyl chain and this alkyl chain, both are the same. So you don't want the same alkyl chain or the same group or the same atom. So this is not chiral. So it doesn't show optical isomerism. So CCl2F2. So you can clearly see on the same carbon you have chlorine, chlorine, and fluorine, fluorine. Same groups. It will not show chirality. Now let's look at C option. So you have CH3, C, OH, C2H5. Yes, this it has a chiral center because you have methyl, you have ethyl, you have a hydroxy, and you have a hydrogen. So this is a chiral carbon. So correct answer will be C. Fourth question. Which of the following is chiral? Yeah, we have a lot of questions based on chirality today because chirality is important. Many questions come every time. So chiral. So 1 comma 1 dibromo propane, chloropropane, right? So this is propane, 1 comma 1 dibromo, and you have 1 chloro. So here you have hydrogens. Here you have hydrogens. You have minimum 2 hydrogens. So this is not a chiral, this is not a chiral, but here you have same bromine groups. This is also not a chiral. So this doesn't have a chiral carbon. Now let's look at C. 1 comma 1 dibromo, 3 chloro propane. So here also you have a hydrogen, right? You have a hydrogen here, and then you have hydrogens here. This is not a chiral, but we have a chiral center here, right? So it has a chiral center. Now let's see this one. 1 comma 3 dibromocyclopropane. So you have a bromine here. 1 comma 3 dibromo, 1 chloro. You have a center of plane of symmetry. You can clearly cut the compound like this here. So it doesn't have like it is achiral. When you have symmetry, the compound becomes achiral. So you have 1 comma 3 dibromo, 2 chloropropane. Yeah, that's the one we discussed now, right? So here, and you have chlorine, 1 comma 3 dibromo, 1 chloropropane. So you have one hydrogen here, one this group, one bromine, one chlorine. You have a chiral here. Did we make some mistake? 1 comma 1 dibromo, 3 chloropropane. Right. It's 3 chloropropane. I'm sorry. I took it 2 chloropropane. Yeah. 3 chloropropane will be like this. So you don't have any chiral centers here. So answer will be B because you have a chiral center here. So fifth question. The maximum number of stereoisomers. This question, the formula might help you. So check the number of chiral carbons. I can see we have 4 chiral carbons. So apply the formula. This is a symmetrical compound and it has even number of chiral carbons. So 2 power n minus 1 plus 2 power n by 2 minus 1 is the formula. So 2 power, you have 4, right? 2 cube plus 2, which will be 10. Easy question. Now, sixth question. Which of the following is meso compound? When you are asked a question with meso compound, check for the plane of symmetry. So you have a plane of symmetry here? No. Because CH3 and ethyl group. You have methyl group, so you don't have a plane of symmetry. Here, you don't have a plane of symmetry because hydrogen and chlorine are opposite. You don't have a plane of symmetry here. Here, you have a plane of symmetry. See here. Now, when you use this plane, then you can clearly see there is a plane of symmetry. Both methyl groups are also on the same direction. So you can see symmetry is there here. So 3 only will be your correct answer. Seventh question. Now, double bond configurations. So let's check for this double bond first. They are asking EZ nomenclature. Okay? Right. Now, for this double bond here, more priority for this carbon. Let's check for this carbon. So you have a carbon connected with carbon here. But here you have a carbon connected with nitrogen. So you have to check for the connectivity. So this will get more priority. So 1. This has more priority. The ring has secondary priority. Right? Okay. Now, let's check for this carbon. You have carbon connected with nitrogen. Here also you have carbon connected with nitrogen. But here you have a triple bond. What is CN? Right? Cyanide group. So you have to treat this like this. So you have multiple bonds you have to treat like single bonds. So this will get the first priority. Okay. So here you have a higher priority on the opposite side. When higher priority is on the opposite side, it will get E configuration. So it has E configuration. Now check for this double bond. So you have aldehyde, so you will get C double bond OH, and you have alcohol COH. So double bond gets more priority because of the connectivity. You have to treat as single bonds. So this will get more priority. Aldehyde will get more priority. Now here, this carbon is connected to a carbon which has double bond. So this will get more priority. And this carbon is connected with normal carbon, and it is again connected to hydrogen. So you have the first point of difference here. So this will get more priority. I'll write simply. So here we got E, right? But here the first priority went to aldehyde and first priority went to this group. So higher priority are on the opposite side, then it will also be E. E comma E will be your answer. Right? Easy. Now, among the following most stable isomer, they gave a cyclohexane. Whenever they ask for stability, check for hydrogen bonding. Right? So there are some other rules also. Let's discuss using during conformational isomerism. So cyclohexane, check for hydrogen bonding. So let's see hydrogen bonding possibilities. So here we can see hydrogen bonding is possible because they are on the same side. So when they are on the same side, hydrogen bonding will be possible. So you'll get OH. So you have OCH3. So because of electronegativity, you will get a delta negative charge, a delta negative charge. Here you will get a delta positive charge. So there is a hydrogen bond here. Okay, this is the hydrogen bond. So hydrogen bond increases stability. So D will be the correct answer. And in other cases, they are on the opposite side or different configurations. You can see in equatorial position and the axial positions. So they won't show hydrogen bonding, so there will be less stable. The most stable will be when they are on the same side. Now, let's see the which question would be eighth. So this is the ninth question. An aqueous solution containing A and B shows optical activity. So A should be optically active and B should also be optically active. A and B are stereoisomers. Yes, that's what we meant. Which of the following possibilities cannot be correct? So they are asking the incorrect statement. A and B are enantiomers. Yes. A and B are diastereomers. Yes, maybe. A and B are not present in equal amounts. Yes. They should not be present in equal amounts. When they are present in equal amounts, they become racemic mixtures. Racemic mixtures are again optically inactive. So this is also correct. So correct option, the incorrect option should be A. Why? A has two centers, but B does not have any because it has symmetry plane. When it has symmetry plane, it will be optically inactive. But in question they are telling B should be optically active. So A should be incorrect. So A option is incorrect. Now, which of the following is D-glyceraldehyde? This is a tricky question. Now, D compounds are when OH is to the right. When OH is to the right. Now, see here. This one OH is to the right, and when you are writing D and L configurations, you have to see that most preferable functional group should be on the top. So aldehyde is the most preferable functional group than hydroxy group. So aldehyde is on the top, so no need to do any exchanges and stuff. OH is to the right, so this will be D. Right? We have all of these also as an option, so you have to check all the options. Give respect to all the options. Now here, you want most preferable functional group to be on the top. So you do a two group exchange once. We have seen just now. When you do a two group exchange once, you have to write the opposite configuration. So let's do a two group exchange. It will become CHO, H, OH, and CH3OH. So OH is to the left. So the configuration when OH is to the left is L. But how did we get this compound? By doing a one group exchange. So, sorry, two group exchange once. When you are doing a two group exchange once, you have to write the opposite answer. You are getting L, so it will be D. So, check here also. You have to, let's interchange these two OH, H, CHO, and CH2OH. So, whatever answer I will get, I have to write the opposite one. OH is to the left, but it will be L. But you did an exchange that two once, two group exchange, you are doing odd number of times. You have to write the opposite. So it will be This compound will be D. So all are D, all are D glyceraldehydes, it will be all. So there is a biomolecule answer also for this, but when we are discussing stereoisomerism, so all will be D. Now geometrical isomerism, this is the 11th question, right? Yeah. Geometrical isomerism is possible. So this is a factual question. In cycloalkanes, because of their less size, they will have uh, rotation can be seen because they have very less size. This is possible only from 3-membered rings to six or 7-membered rings. So when it comes to more than seven member of rings, geometrical isomerism can be possible. So this is a factual question. Answer will be D. You can check Cengage for more details on such kind of questions. Now, 12th question. Which of the following is correct set of physical properties and geometrical isomers? So this is a tricky question. Now here you can see dipole moment is like this. Here you can see dipole moment is like this. Chlorine gets more larger vector. So using common sense, you can see that here there is a larger vector, a very big vector. Chlorine is highly electronegative and carbon is very small. Okay. Now let me draw that. So the net resultant will be, we have opposite direction, right? So the net resultant will be towards here. Okay. Now, in case of this one, so you have more here and less here. So parallelogram law, right? So in which case the dipole moment will be more. So in case one, the dipole moment will be more, right? In case one, the dipole moment is more. You can calculate the dipole moment using the bond angle also here. So anyways, you can clearly see that the dipole moment is more in case one than in case two. When dipole moment will be more, so you have two options here. Boiling point will also be more. So dipole moment is directly proportional to boiling point. See, we have the same options. When it comes to melting point, this is a trans-like compound, but here it is like a cis-like compound. This is a trans-like compound, it is cis-like compound. In trans-like compound, stability, like packing will be more. Packing will be more, melting point will be more. Okay, so 1 is greater than 2. Answer will be C. So it is a trans-like compound, it is a cis-like compound. In trans-like compounds, melting point will be more and stability will also be more. And dipole moment you can calculate and you can use using common sense, 1 will be greater than 2. So the correct option will be C. Now this question, 13th. Which of the following are chiral? So here you can see center of symmetry is there. This will be achiral. Here, center of symmetry is not there because you have a extra chlorine group here. So this will be chiral. Now here, there is no center of symmetry, right? There is no center of symmetry. So this will be chiral. Here you have center of symmetry. When you are going here, you are reaching the same groups. When you are going in the opposite directions, you are reaching the same groups. So this is achiral. So 2 and 3 are chiral, right? C will be your correct answer. So we have find the number of chiral carbons in the following compounds. So here you have hydrogen. This is not a chiral. Okay. So here you can see this is a chiral. You have a methyl group, you have some chain here, and then you have a OH group and a H. So this is a chiral carbon. And this is also a chiral carbon. You have some chain here. You have a hydrogen, you have a hydroxy group, and you have another chain. So all are different sp3 hybridized. You have two chiral carbons here. And here you have same hydrogens. When you have the same atoms of same groups, it will not be chiral. Right? Now, you have two here. Let's check here. So this is a tricky question. Here you have CH3. Here also you have CH3. So this is not a chiral. Here you have hydrogen same. This is also not a chiral. This is also not chiral. You don't have chiral carbon here. 0. So 2 and 0. Answer will be C. But check here also. For just mandatory purposes. So you want one chiral carbon here. Right. This is one chiral carbon here. I can see. You have a ethyl group. Okay. And you have one isopropyl group, and you have a CH3 group, and you have a hydrogen. See, you have one chiral carbon here, 201. That will be the answer for the 14th question. Now let's see the 15th question. RS configurations. So you have to follow the SIP rules. So numbering, you'll start from here. 1, 2, 3, 4. Okay. Now let's discuss for the second carbon. So I'm drawing second carbon differently. So you have CCl, C2, Cl, H4. Okay. And then you have OH, H, C2, H4. So this is the second carbon. Now, giving the priority, oxygen will get the first priority, and then carbon is connected to hydrogen, carbon is connected to chlorine. So connectivity you have to check according to SIP rules. This will get the second priority. So here, this will get the third priority, and this will get the post priority. Here, the least prior group is on the horizontal. So whatever answer you get, you have to change it. Okay. Now, here you can see it is clockwise. Clockwise is R, but the least prior group is on the horizontal, so you have to change it. It will become S. So 2, you are getting S. Right? 2, you are getting S. So you can eliminate these two options. So here. Now check for the third one. So you have C3, H7, O. And then you have chlorine, hydrogen, and CH3 here. Hydrogen is again on the horizontal. So you have to change the configuration, whatever you get. So giving the priorities, so chlorine get the first one. This will get the second one because this is CO and CH. So again, you are getting clockwise. Clockwise is R, but hydrogen is on the horizontal. You have to change it to S. Okay. So R is turning into S. So you have 2S, 3S. What is the correct answer? A. Now, the following two compounds are, you can clearly see their geometrical isomers because with respect to this double bond, you are changing it is cis or trans, right? And the number of carbons are same. And then they are not conformers because they are not rotating. And then they are not structural because the carbon chain is the same. And then they are not identical also because the spatial arrangement is different. Of course, there will be geometrical isomers. Now, the last question, 17th question. The compounds are best described as. So you have two methyl groups above the plane, one methyl group below the plane. Two methyl groups above the plane, one methyl group below the plane. So here you can't say cis trans because you don't have a stereogenic center and you don't have same number of carbons between each groups. So there should be positional isomers because the position of methyl groups is different, right? So they should be positional isomers. The answer is none of these. So these are the 17 questions. So in the next video, let's discuss some advanced question. Again, we will discuss some 15 questions. Right? Thank you.